Okay, the recording is now on. You can go back and start the class in a few minutes. So this is what we looked at yesterday, the Euclidean algorithm. And this was supposed to help us find a faster way to obtain the greatest common divisor of two integers. So we looked at this example and explained the details of the example. So what we are going to do now is to look at why this should work. We are going to look at the general situation, why this one should work. Okay. So the reason why it works is the following theorem. It says if A is equal to BQ plus R, where A, B, Q, and R are integers, then the greatest common divisor of A, B, and the greatest common divisor of B, R are equal. So that's what we need to show, that if this relationship holds, this equation is true, A is equal to BQ plus R, then the GCD of AB will be equal to the GCD of BR. So, and when we apply this repeatedly, we keep reducing the problem of getting the GCD of two large numbers to a smaller problem of getting the GCD of two small numbers. So our strategy is this. If you want to prove this, we need to show that the common divisor of A and B are also the common divisors of B and R. That's all we need to show, because if the set of common divisors is the same, then the greatest, the largest divisor will be the same for both pairs. Okay, so let's see if we can achieve that in our proof. So we pick any common divisor of A and B, and we call it D. So suppose D is a common divisor of A and B, then it means we can write both A and B as multiples of D, so that A will be equal to KD and B will be equal to SD. And we can rewrite the initial statement. The initial statement was R is equal to, A is equal to BQ plus R. We can rearrange it so that we have R is equal to A minus BQ. And we know what A is. A is KD. We can make that substitution. We know what B is. B is SD. We make that substitution. And this will be equal to D multiplied by K minus SQ in brackets. So what we have done, we've been able to write R as a multiple of D, yet and D was a common divisor of A and B. So any common divisor of A and B will also divide R. Okay. So that means any common divisor of A and B turns out to be also a common divisor of B and R. So on the other hand, if D divides both B and R, then again, using the same arguments, Turi, can you please mute your microphone? So on the other hand, if we take a common divisor of B and R, then it's possible to write, let's say the common divisor is D, then we can always write B as a multiple of D and R again as a multiple of D. And using our statement again, we have A is equal to BQ plus R, and make the substitutions for B and R as SDQ and SD and TD. This simplifies to D into brackets SD plus T. So again, we have found a common divisor of B and R, and we have shown that that common divisor of B and R is also a divisor of A. And therefore, any common divisor of B and R must also be a common divisor of A and B. So what have we shown? Essentially, we have shown that the set of common divisors of A and B is the same as the set of common divisors of B and R. So if you're looking for the largest common divisor from the same set, you will end up with the same answer. And therefore, this means that the greatest common divisor of A and B will be equal to the greatest common divisor of B and R. So what this means is, instead of struggling to find the greatest common divisor of A and B, which will be there'll be two larger numbers, we focus on finding the greatest common divisors of B and R, which will be smaller than A and B. Now this can be repeated over and over again until you get the smallest possible pair that you can work with, as we saw in the example. So this result is what makes the Euclidean algorithm work. So we shall now describe the Euclidean algorithm itself. Now, if we have two positive integers where A is larger than B, we can relabel them so that we call A R0 and we call B R1. So we repeatedly apply the division algorithm to obtain the following. So we write R0 is equal to R1 Q1 plus R2, where we again insist that the remainder cannot be bigger than the divisor, so that R2 will be less than. Now this is a mistake. R2 should be strictly less than R1. I will have to correct that on the slides. So we have 0 is less than or equal to R2, but R2 must be strictly less than R1. The same applies to all the other inequalities that follow. So we repeat this. Now what we have done for R0 and R1, we do for R1 and R2 in the next line. We apply the division algorithm to R1 and R2, so that R1 will be equal to R2 Q2 plus R3. So here what we have is again that 0 must be less than or equal to R2, and strictly, sorry, this is a mistake. 0 must be less than or equal to R3, and R3 must be strictly less than R2. So again, I'll make those corrections before I share the slides. So we keep doing this. So the next pair that you will look at, if you are to continue, would be R2 and R3, and keep going on until you end up with a remainder 0. Now in this process, the last non-zero remainder, which is here, this Rn, is what you get as your last non-zero remainder. That will be the greatest common divisor of A and B. So you can see that from here, based on the theorem that we stated earlier, we have GCD of R0 and R1 must be equal to GCD of R1 and R2. We keep applying that until we get to the end. At the end, the remainder is 0. So we have Rn minus GCD of Rn minus 1 and Rn will be the same as the GCD of Rn and 0. But the greatest common divisor of Rn and 0 should be equal to Rn, not 0. Again, there's a mistake there. Looks like today the slide is full of mistakes. So the GCD of Rn and 0 should be equal to Rn.
So no need of typing.
So we come to the conclusion that the GCD of A and B must be equal to Rn. This is the last non-zero remainder in the sequence of division. Jen Kavata, please mute your mic. Good, thank you. So now we can proceed. This was just the description of how the Euclidean algorithm works. And the theorem we proved earlier, this theorem is what shows why it works. And the reason it must come to an end is because these numbers R0, R1 are decreasing. So eventually the process will stop. So some corrections here I've made. This GCD
Pardon, sir, I'm not getting.
will be Rn. Pardon? You can't hear me? Is there anyone else who cannot hear?
Yes.
You can hear me or you cannot hear me?
He can hear you, but he cannot understand.
Yes, you will have to listen to this again. I told you a lot of these things you have to read more than once.
We cannot hear you, sir.
Pardon?
I cannot understand.
Now, gentlemen,
We cannot see your screen.
so if you walk in expecting to understand at the first look, it's going to be a little difficult. So this is something you will have to sit down and read again on your own. You will not understand it the first time. You should not come to university with those expectations to understand things the very first time you look at them. If that was the case, then you would not need to come to university. So you have to have some patience. You will have to pull this aside and read it for some time on your own. Eventually, it will make sense. You just need to learn to be patient.
Thank you.
I also did not understand it the first time I read it. So you will need to put in the time. And the video will be shared, so you'll have a chance to watch and repeat the video.
Thank you, sir.
Yes. Okay. So let's apply, when we apply this to an example, maybe we'll see what is going on. So we are going to use the Euclidean algorithm to find the greatest common divisor of 414 and 662. So 62 is the larger of the two numbers. So we apply the division algorithm to get 662 is equal to 414 times 1 plus 248. So the next step is to apply this to the two smaller numbers, that's 414 and 248. So when you apply this to 414 and 248, we have 414 is 248 times 1 plus 166. We repeat the same step for 248 and 166. And when we apply the division algorithm, 248 is equal to 166 multiplied by 1 plus 82. Now we apply this to 166 and 82. And then we have 166 is equal to 82 times 2 plus 2. Then now we apply this to 82 and 2. And then we have 82 is equal to 2 times 41 plus 0. So the last non-zero remainder here is 2. And that will be the greatest common divisor of 662 and 414. Now this is a small example, rather a simple example, which you may be able to solve using other techniques that you've learned earlier. But the idea here is to show you how the process works. So if these were larger numbers and you have to use a prime factorization technique to find the greatest common divisor, it can be a little more difficult because you may not be able to find all the prime factors easily. It can take you a long time to get all the prime factors. But if you use this method, you do not need to know the prime factors. Just repeatedly apply the division algorithm and you pick your last non-zero remainder to be the greatest common divisor of the two numbers. In this case, the two numbers are 662 and 414. So this process is the same process that is described in an abstract way in the previous slide. So that same process is a process we're applying to the two numbers, 662 and 414. So by now it should be making at least some sense, if not complete sense. It should be making some sense. So there are three things you have to connect. One is this result, that the GCD, if A is equal to BQ plus R, the GCD of A and B must be equal to the GCD of B and R. So that's the result you need to connect. You connect it to, if you move now to, this is the proof. So if you have two numbers, like here we said A and B, we rewrite we rewrite this using the division algorithm, so that R naught, first of all, relabel the numbers so that A will be equal to R naught and B will be equal to R1. So if we label them with numbers, it's easier to track them as we proceed. So we write R naught is equal to R1 Q1 plus R2. That is this first line here in the set of equations. So this is true, and we insist that R2 must be strictly less than R1. So after that, we apply it, since we know that the GCD of R0 and R1 is the same as the GCD of R1 and R2, we now apply the same process to R1 and R2. So R1 and R2 will be R2Q2 plus R3. Again, here it's the same idea. Since we know that the GCD of R1 and R2 is the same as the GCD of R2 and R3, we now apply that process to R2 and R3. So we are not losing anything by repeating the process. We still retain our GCD until we get to the last step. Now, from the last step, we can conclude that the GCD of Rn minus 1 and Rn should be equal to the GCD of Rn and 0. And the GCD of Rn and 0 is definitely Rn. So in this process, you will get your greatest common divisor as the last non-zero remainder in this algorithm.
Excuse me, sir, just the button.
Yes.
Please repeat that part. The last part.
What is the last part?
Starting from Rn minus 2 is equals to Rn minus 1 Q2, that one.
Yes. So now this one, you are simply, you keep going down until you reach the zero remainder. So we don't know what n will be. It depends on the numbers that you pick. So this process can go repeatedly until it will have to stop at some point after n steps. So that's where we stop. Now, before this Rn minus 2 and Rn minus 1, there will be another one before that. So these three dots indicates that this process is still continuing. There are some steps you have skipped. So we have written the first two, and now we skipped the in-between steps, but we know the pattern in which we are constructing these equations. So we know what will happen in between. And then we've written the last two, assuming that it stops after n steps, right? So the property we are using is that the GCD of R0 and R1 will be the same as GCD of R1 and R2. So it means we can apply the division algorithm again to R1 and R2. And then when we do that, we know the GCD of R1 and R2 is the same as the GCD of R2 and R3. So this is the same thing that happens all through. Even up to the last step, the GCD of Rn minus 2 and Rn minus 1 is the same as the GCD of Rn minus 1 and Rn. So you apply the process again to Rn minus 1 and Rn. And here now, the remainder will be 0. So you stop when the remainder is 0. You can't tell at what point it will stop. That depends on the numbers you pick. So for some numbers, it will happen faster. For some, it will take longer. But eventually, the process will stop. And once you get a 0 remainder, you have to go back one step. This last non-zero remainder in the second last step becomes your greatest common divisor. And why that happens is explained in the next paragraph. So is your question answered now? So the best way to learn is
Correctly.
to pick your pen and paper. Once I share the slides, you try to write these things down. The other thing you need to do is go to chapter 4 of the book I shared and read that chapter. Like I said, this thing cannot work from me just talking. You can't learn maths from me talking. You have to do your own writing. So you have to make the effort. But of course, if you have questions, you can ask. So I don't need to repeat this. I think you have understood this one. So it's the same process in the previous slide, but now we have some two concrete numbers that we are working with. Hey, the person who asked the question, you have gone quiet. Have you understood?
Yeah, I have understood it correctly now.
Tuko pamoja sasa.
Yeah, we have understood.
Even Felix has joined you. Good. So now
Repeats.
Let's continue. Now you will have to watch the video again. I will not repeat now. Once you watch and try to solve on your own, you will encounter some problems, and then you can ask me questions on the sections where you encountered problems. Otherwise, we will not move. So this theorem that follows says if A and B are positive integers, then there exists two integers, S and T, such that the greatest common divisor of A and B will be equal to SA plus TB. Okay? So this simply says if you know the greatest common divisor of A and B, it's always possible to find two other integers such that you can write the greatest common divisor of the two numbers as SA plus TB. Umeelewa?
No.
Okay. So now we show this using an example. We have these two numbers. The two numbers are 6 and 14. And we know that the greatest common divisor of 6 and 14 is 2. And we can see that it's possible to write 2 as -2 times 6 plus 1 times 14. Munaelewa hiyo?
Yes.
So we are, the next step is going to show us how we can find these two numbers, these S and T. So in this case, I picked an example that we already know what S and T will be. So the next step is showing us how to find those two numbers. And that's what we are going to get into now. Once you have the GCD, how do you find the two numbers S and T? Again, we'll pick a simple example so that it becomes easier to explain. So here we have two numbers, 252 and 198. And we are asked to express the greatest common divisor of the two numbers as a linear combination of 252 and 198. So we will apply this Euclidean algorithm to the two numbers to find the GCD. And when we do that, we apply first to 252 and 198, then to 198 and 54, then to 54 and 36, then to 36 and 18. And at this point, the remainder is 0. So our greatest common divisor will be 18. The last non-zero remainder here is 18. The second last step is the one that gives us. So this one we're able to do in exactly 4 steps. Now, just hold on. So there is how we get S and T is you have to start working backwards. There's a line here that you will not see clearly, but I will state it at the bottom of the slide. There's a line that was taken a little too low, but I'll fix it in the before I share. So in this line, we start by working backwards. We start from the second last line. We see that 54 and so I lost connection, but now I'm back again. I don't know if you can hear me now.
Yes, but you can see
Yes,
us.
we can.
Yes.
Okay, I'm sharing the slides afresh.
Yes, but not understanding.
That one, like I told you, now you
We
have
are
to
not understanding, please.
realize you are at the university and you don't expect to understand anything the first time you see it. Okay? So you have to take time. You will go and read through this. You have a textbook I shared with you. You will go and read the textbook as well. And you will have questions to ask. So you have to learn to read. There's no shortcut here. That's how it's going to work. So, and the only way you learn is by trying to do this yourself. So right now, I'm leaving the slides on the screen for a while. And if there's something you see you cannot understand, pick your pencil.
Yes, sir.
Pick your pencil and paper and try to work it out on in your book. Okay. So the only way you learn mathematics is by writing. You cannot learn it by staring. So pick the book, write out a few things, and see how it works. So some of these you have the calculator, so it's easy for you to compute. You don't have to compute them with your directly. So make use of all the tools you have. Use your book, use your pencil or pen, and use your calculator. There's no shortcut to this. You cannot stay at mathematics. You have to learn by writing. So try to work this out. I'll give you 3 minutes to do this. Then we continue. So just follow the steps for the Euclidean algorithm. You repeatedly apply the division algorithm at each stage until you get a 0 remainder. Then the GCD is the last non-zero remainder. Yes, the last non-zero remainder is 18. So using the second last equation here, we can express 18 as a linear combination of 54 and 36. So here you simply make 18 the subject. So 18 will be equal to 54 minus 1 times 36. So that's what you have here. Now, but we know that 36, if we go back to this step, now the second step here, we can see that 36 can be written as 198 minus 3 times 54. So this dot here means 3 times 54. And here we can just make 36 the subject. And the first equation we set up was 18 is equal to 54 minus 1 times 36. So I can replace this 36 in my first equation by this expression, which is 36 is equal to 198 minus 3 times 54. That is what appears in the next step. So I had 36 here. I have replaced it with 198 minus 3 times 54. So if I put all the like terms together, I have a 54 here, and this negative and negative will give me plus 3 times 54. So if I put all of them together, I have 4 times 54. But I have only one negative 198. So I write it here as negative 1 times 198. Again, the aim was to write 18 as a linear combination of 54, or rather, as a linear combination of 252 and 198. So now I already have 198. I don't need 54. I have to find a way of writing 54 in terms of 252 and 198. So we'll go back one step. If I look at the first line, I can write 54 as 252 minus 1 times 198. So I make that substitution for 54. And the next step, I have 18 will be equal to 4 times. So I'm replacing this 54 here with 252 minus 1 times 198. Then I subtract 1 minus 198. So now I have all the numbers I needed. I just need to put the like terms together. I have 252 and I have 198. So I rearrange this so that there are 4 252s. Then if you open up the brackets, this will be minus 4 times 198 minus 1 times 198. So this can be eventually written as 4 times 252 minus 5 times 198. And this completes the solution. Now, this solution is not unique. There are many other integers other than 4 and negative 5 that will work. So in this case, your S and T will be 4 and negative 5. So the S and T I'm referring to is what was in the initial theorem. The initial theorem says that you can write the GCD of A and B as S multiplied by A plus T multiplied by B. So in our example, A is 252 and B is 198. And we've been able to find S to be 4. If you look at the very last equation down here, S is 4 and T will be negative 5. It's possible to find other values of 4 and of S and T that work, and we shall explore that later. So here is another theorem that we will do. I think this might be the last, probably the second last theorem we shall do. So the theorem says the following: if A, B, and C are positive integers such that their greatest common divisor, the GCD of A and B, is equal to 1, and A divides the product of B and C, then A must divide C. So clearly, since the GCD of A and B is equal to 1, A cannot possibly divide B. And what this says is if A divides B with another number C, then A must divide C. We're going to prove this. Please mute your mic so that. Emmanuel. There's a gentleman called Emmanuel who is not muting the mic.
Can you please repeat the previous slide?
Pardon?
Can you please repeat the previous slide? I was copying and it disappeared.
You are doing what?
I was copying.
So do you want me to leave it on for which one? This slide?
No.
This one?
Yeah, this.
Okay. Can
Only
you
1
write
minute, please.
But the video will be available later. So
Let them to screenshot.
Okay, yes, I've screenshot it.
you are done?
Yeah.
Okay. So we want to prove this theorem. It says that if A, B, and C are positive integers, such that A and B are relatively prime, that is the GCD of A and B is equal to 1. And it also, and we also given that A divides the product of B and some other integer C, then A must divide C. So the proof, we use some information that we already have. We know that the GCD of A and B is equal to 1. That is given in the theorem. Now, based on this and the previous theorem that we just proved, we know that we can find some two integers S and T, such that the GCD, which is 1, can be written as SA plus TB. So we don't need to know what S and T are here, but we know that they can be found. Now we can multiply both sides by C to obtain C is equal to CSA plus CTB. And we rearrange it so that we have C is equal to CSA plus TBC. Now, also in the theorem, we are told that A divides BC, right? So I can write BC as a multiple of A, and I substitute that in the equation to get C is equal to CSA plus TKA. Now A is common, so I can pull it out so that I'm able to write A, C is equal to A multiplied by CS plus TK. So I've been able to write C as a multiple of A, and therefore that means I have shown that A divides C. So that's basically what it means. We have shown that C must be a multiple of A, and therefore that means A divides C. And this will be true if the first two conditions hold. The first two conditions hold, and that is the condition that the GCD of A and B is 1, and that A divides BC. If those two conditions hold, then A must divide C. So we have proved that one. So the same idea can be extended to the following theorem. We generalize it. So this one says that if P is a prime number and P divides a product of n integers, A1, A2, up to n, AN, where each AI is an integer, then P must divide one of these integers. There must be at least one of the integers. There can be more, but there must be at least one of the integers that is divisible by P. So that's what this theorem says. The proof is left as an exercise to the hardworking students of SMA 108. This theorem can be used to prove the uniqueness of the prime factorization of a positive integer. We saw earlier that any positive integer can be written uniquely as a product of prime numbers in increasing order of size. So this theorem can help us to prove that that product is unique. I think we can stop there for today. We have only a few minutes left. I don't want to start the next slide. So if there are any questions, or if there's any part you think we need to, but there's only 4 minutes. I don't think there's time to go over anything. You have any slide that you have questions on?
Yes.
Which one? I keep going back.
The last slide actually about the previous.
Here.
Yes.
So what is your question? There's someone called Felistas who is has unmuted the mic. Can you please mute your mic?
I don't want to be a victim without grade. I want to read.
So what is your question?
Okay, student, can you hear me well?
You have gone quiet. You had a question. Who was asking the question?
Excuse me, sir.
Yes, Margaret.
I was asking that you repeat the part for finding S and T.
So I don't understand this part. So you want us to start
by what scale?
Felistas, there's someone called Felistas who's making noise for us. Felistas, Felistas.
Gosh. Here in the status.
Can someone talk to Felistas and tell her to mute the mic? I think she's updating her Instagram.
Felistas, mute your mic.
Hey, okay, let me mute her myself.
Felistas.
It's okay, I will mute her. I think
Felistas, see me the class.
Pardon? You know, the time for the class is over. I'm just repeating this part for those who want to listen. But the class is over. Those who would like to go can go, but you can don't make noise for us. Applications of here we are saying the following. If we know the greatest common divisor of two numbers, the theorem claims that it's always possible to find two integers, that is, we call them S and T, such that the GCD of the two numbers will be equal to SA plus TB. So we have not given the proof for this theorem, but we have illustrated it using an example. So in the example, take A to be 6 and B to be 14. And clearly you can see that you can write the GCD of 6 and 14 is 2. And you can see that it's possible to write 2 as negative 2 times 6 plus 1 times 14. Right? So here you can take your S to be negative 2 and your T to be 1. So the question is, how do we find this S and T? In this case, we have given an example where it's known beforehand so that you can see that it can work. But this example is not a proof. It is just an illustration of the theorem. Maybe later on I can work out the proof and share. So we can use that to express the GCD of 252 and 198 as a linear combination of the two numbers, 252 and 198. So I need to find two numbers. One I can call S and the other one I can call T, such that the GCD of 252 and 198 will be equal to S multiplied by 252 plus T multiplied by 198. That's what I'm looking for, right? So I can apply the Euclidean algorithm first to find the GCD. I think that one you should have, by now you have understood. And we can see that the GCD is clearly 18. So now we work backwards from 18. We write 18, make 18 the subject here, so that 18 will be equal to 54 minus 1 times 36. That is the first statement here. It's a bit low on the slide, so you can't see it. But 18 is equal to 54 minus 1 times 36. Okay. So I can go further and replace 36, because I can, in the step above that, I can write 36 as 198 minus 3 times 54. So that's what I do in the next step. I replace 36 by 198 minus 3 times 54, and rearrange the terms to put the like terms together. So we have 4 54s, and there's a negative 1 times 198 there. So we just put the like terms together. It's still a problem because what I need is 252 and 198 on the right hand side, but I still have 54.
Excuse me.
Back, yes.
There we have negative 3 times 54, and the other side, oh, I've gotten.
So some of these things you need to write them down. When you write them down, they become very clear. Don't be shy to write them down. Chukua kalamu bwana uandike. But it's good you have understood. So using
Hello,
the same
sir.
process,
Where did that 4 come from?
which 4?
4 times 54. Your 4 umetoka wapi?
Andika na kalamu uone mahali imetoka. Right? Umechukua kalamu? I want to tell you what to write.
Yes, I have a pen.
Yeah, okay. Now write down the following. Write 54. Just rearrange this thing so that you have 54 minus 198 plus 3 times 54. When you remove the brackets, that's what you get, right? You have 54 minus 198 plus 3 times 54. Remove the brackets completely. Tuko pamoja?
Yes.
Yes, sir.
So now 54 is common. You can write 54, and then in the brackets, you put 1 plus 3. So it's 54 multiplied by 1 plus 3, and 1 plus 3 is 4, right? And then all that minus 198.
Oh, sasa nimefahamu.
Hii ni hesabu ya class 8 bwana. Umesahau? Umesahau hesabu ya class 8?
Sasa akili kidogo imechoka bwana.
Au kukunywa chai ya saa 10?
Bado.
Okay, so I think now you have understood. Do you still need more explanation?
No, I'm okay. Yes, sir.
Okay.
Thank you.
Good. So the process is the same for the rest. So eventually you want to have 18 on one side, and the right hand side you want it to be in terms of 252 and 198. So you just work backwards from this division algorithm until you have everything on the right hand side in terms of 252 and 198. Tuko pamoja?
Ndio.
No, kuna ule aliuliza swali amenyamaza.
Yes.
Umeelewa?
Yes, sir.
Good. Yes, sir. So now you can allow me to leave?
Yes.
Yes. That's a weekend.
Another weekend leo bana.
Thank you.
Early for the weekend.
Have a good evening.
Okay,
Have
you
a
too.
good
Have a
day.
good evening.
Thank you. Goodbye.
Tupatane next week.
Yeah, we'll meet next week.
Same.
Yeah.
Things are very interesting.
Very much interesting. George.
Yeah.
First learner.
Mavaslana ndio sisi.
You can't exist. You can't.